Okay, last time we discussed the biasing techniques. So we basically discussed biasing methods. So first we found that the very simple way of biasing, fixed bias. So then we found that, so in addition to this fixed bias, we introduce a kind of a resistor to the emitter. So we found that it's a kind of a emitter bias. So third one actually, so instead of this emitter resistance, we introduce, or in addition to this emitter resistance, we add a resistor in between this collector and base junction. So it basically identified as a kind of a collector feedback bias. So feedback bias. So the fourth one is actually the common way of biasing most of the transistor circuit. So this voltage divider bias. So voltage divider. So these are the common type of biasing methods. So we know that biasing is a kind of a process to make the operating point of the transistor at a given position. So we know that, so we have this device characteristic. So it's depend on the transistor. So we have device characteristics. So for different base currents, so we have this kind of arrangement. So this is the device characteristic. It depends on the transistor and it's unique for the transistor. So once you get the data sheets, you can easily pick this device characteristic from the data sheets. So then we found that, so in addition to the device characteristic, we have another kind of a characteristic. So we have device characteristics. So the other one is the circuit characteristic. So the circuit characteristic is basically explained by the DC load line. So this DC load line itself give a kind of an indication about how this VCE and IC, those are output parameters. So how those two parameters are vary for the given circuit. So this basically gives how the transistors collector current and collector emitter voltage basically varies with respect to its own properties, and at the same time we can get a kind of a model to explain the circuit characteristics, how this output circuit parameters VCE and IC behave for the given circuit. So whatever the circuit characteristic is again a function of the resistors and the supply voltage we basically power up and connect to the circuit, and DC load line gives the exact idea about the output characteristic of the circuit, how this collector emitter junction voltage and collector current varies. So what we can simply do is we take the device characteristic from the data sheet and we overlay the circuit characteristic or the DC load line on top of that one. So then we can basically identify where we can place our operating point of the transistor. So it basically depends on our requirement. So according to our requirement, we can basically select what would be the Q point base current. According to the Q point base current, we can simply place our Q point on the active region, or else if you are planning to design a kind of transistor switch, so you can think of where we can play toggle the Q point in between this cutoff and saturation. So how would be the base current, how would be the collector emitter junction voltage for this kind of arrangement. So everything depends on our requirement. So depending on our requirement, we can place the Q point. So to place the Q point at a given location of this operating region, so we introduced couple of mechanisms. So those are the biasing methods. So we just go through this very simple mechanisms of biasing: fixed bias, emitter bias, collector, feedback bias, and voltage divider bias. So these are very common ways of biasing or placing your the transistor Q point on an active region. So then we found that, and we conclude that so by changing the resistance, we basically placed on this base terminal or the collector terminal or the emitter terminal. So those parameters are heavily influenced to the real operating point of the transistor. At the same time, the supply voltage also. So by adjusting or carefully design or selecting those values, so you can manipulate the operating point of the transistor. I mean, it means like you can adjust your Q point according to these the values of the selected resistors and the supply voltages. Okay, so at the same time, we found that to obtain this DC load line, so first we have to get the DC equivalent circuit. So the equivalent circuit means like, so we have this actual configuration. So actual circuit configuration. So from this actual configuration, so we basically do this kind of a modification. All capacitors are replaced with open circuit, and all the inductors in the circuit are replaced by the short circuit element. So once you replace these capacitors and inductors, so then basically whatever the circuit diagram you will get is the DC equivalent circuit. So if you want to analyze or if you want to bias a transistor circuit, first you have to get the DC equivalent circuit. So then only you can apply whatever the equations and get some relationship between this current voltages and resistors and design or try to find the exact operating point of the transistor. Without this DC equivalent circuit, you cannot do anything related to biasing. You can do it, but whatever the answers or the conclusion you made is completely invalid if you are not getting this correct DC equivalent circuit. So this is the very important point. Yes. So then, so we found that most of the examples we discussed, we have different, I mean, we have capacitors placed in the circuit. So we found that there are some capacitors in the collector and the load, in between the collector and the load, like this. So this is some capacitor. So this is the collector. So this is the collector of the circuit, and this is the load. So this is the emitter and this is the base. And most of the time, whatever the input signal, so we know that this transistor can be act as amplifier. So once we bias the circuit, we can amplify external input. So this external input is basically connect to the circuit through a kind of a capacitor. So those are like at the same time, this load, whatever the external load is also connect to the collector through a capacitor, and the input, whatever the external input, also connect to the circuit through a capacitor. So those are basically identified as coupling capacitors. So it basically either input or either the output is basically connected to the transistor circuit through the coupling capacitors. And again, in some circuits you may found that there may be some capacitors which basically connect to the emitter and the ground. So like here. So those are known as bypass capacitors, and the capacitors which I explained previously, those are defined or identified as coupling capacitor. So what's the real importance of this coupling capacitors and bypass capacitors? So for example, now we know that, so for example, let's think about this decoupling capacitor you basically place into the input side. So we know that once we bias the transistor, so this is the variation of the base current. So we have this. So this is IBQ, the base current at Q point. So this is your base current. So now this transistor is basically placed at this point. So this is IBQ. Now we want to connect a kind of external signals to amplifier. So let's assume this is the amplified, this is the signal which we need to amplify. Okay, so if you basically plug this I in to the base, so this is the output of the circuit. So it simply superimpose on top of this Q point base current, and this is the output. So this is the actual base current now, IP. So this is the actual base current. It basically has two components. One is a DC component, which is come from the biasing, so IBQ. So in addition to that, so this is actually IBQ plus this I in. So this is the input current we get through the external source, and this is the Q point current. So whatever the ultimate current flow through the base is just the sum of this DC base current or the biasing base current plus the external input. Okay, now this is your, so this is the biasing base current, and whatever the input in is on top of this one. So let's think about this. So this is your input. So this is actually, so this IB, which I am referring here. So according to that, you may get a kind of a proper amplification. So what happens in addition to this I in, so due to certain reasons, so there may be a chance of getting this input signal offset. So let's assume there is a DC offset. So then input current is something like simply offset by the signal. So this is the signal. So this is like with a kind of with a offset. So due to some reason, so the actual input becomes a kind of input plus a kind of a delta amount of offset. So this is a kind of a DC offset due to some reason, like your input is simply distorted and it shifted to upward due to the whatever the induced DC offset. So this is the actual input we need to amplify. So this is kind of a actually error which incurred on top of this input. So if you directly feed it to this circuit, transistor circuit, so this DC offset, simply change the Q point base current. So this DC offset influence to the Q point, because it's a kind of a DC component, so it immediately affects to this initial biasing base current. So whether we place the Q point to here, due to this offset, so this Q point is simply moved to somewhere here. So now the Q point is actually there, and your amplification is on top of that. So then whatever the output also basically influenced by this DC offset, because the original Q point is shifted along this DC load line due to this additional offset. So that also basically reflect and convey through entire amplification circuit, and at the output also we have a reasonably high amplified DC offset due to this initial offset introduced through the input. So if you basically connect a capacitor in series with the source, so this is in series with the source. So what happens? So we know that if it is a DC signal, so this capacitor acts as a kind of an open circuit. So it means like if you basically introduce this kind of a DC AC signal with a kind of a DC offset to a capacitor, so this capacitor basically drop this offset and you will get this kind of a pure symmetric signal. So it basically extract the AC component and drop the DC component. So it's extract the AC component and remove the DC quantity. So this is the simple phenomena of the capacitor. So it simply block the DC and pass the AC signal. So then we know that if your input signal is basically having a DC offset, once you connect a capacitor in series, so this capacitor is able to drop this DC quantity and extract the AC quantity only. So then whether you add this kind of a signal with a kind of a DC offset through the capacitor, so this capacitor is extract the on this sinusoidal or this AC component only and fed to the base. So then we can guarantee that, so we are getting a AC component only to the transistor amplifier. So then we can assure that the Q point we set it through this biasing process remains as it is. No any impact to the biasing due to this external source fluctuation, because we introduce a capacitor to block whatever the DC offset introduced by the source. So it's a kind of a blocking this DC component and absorbing the AC component only, which we need to amplify. So basically we want to amplify the AC component only, not the DC offsets. So if you just couple the source to the transistor circuit, so you will definitely ended up with a kind of a amplified offset as well. So then the whatever the output would be simply distorted due to this amplified DC offset. So you can basically remove this DC offset by introducing coupling capacitor. So either you can connect to the input, so then basically through this input coupling capacitor you can remove this the impact of this DC offset introduced by the input signals. At the same time, you can connect this coupling capacitor to the load. So then whatever the reason, due to whatever the reason inside this amplifier, so there may be a chance of introducing this kind of a DC offset to the output signal as well. So we can simply drop this introduce offsets due to this transistor or amplification process, uh, and we can drop those offsets pass into the load. So then ultimately your load also simply get a pure amplified version of your input, and whatever the offsets introduced by the amplifier simply drop or remove through this coupling capacitor. So this is the real reason of having this coupling capacitors to the input and output side, just to block the what unnecessary DC component. So what happens like then what about this bypass capacitors? So what's the reason of having this bypass? So it's basically connected to the circuit in parallel. Okay, so we know that if it is a capacitor, so this capacitor acts as an open circuit to DC signals and act as a short circuit to AC signals. So if you basically add a kind of AC signal, capacitor is capable of extracting this AC and drop this DC component. So there may be chance of, like for example, due to this thermal noises and uh, kind of noise, due to some noise effects. So if this is your emitter current, so this is the amplified version. So this is the amplified version. So this is IEQ, and this is actually the amplified version. And due to some internal noises, due to some thermal effects or due to some imperfect electronic component, there may be a kind of a noise introduced within the circuit. So due to this noise, your output is something like that. So this noise is simply superimposed on the whatever the required signal, and it's basically distorted by this noise. So then whatever the required pass kind of a noise. So this is a kind of a noise. Noise is actually high frequency random signal. So then what happens if we apply a kind of a high frequency signal to the capacitor? So this high frequency signal, if you introduce a high frequency signal, we know that the impedance of the capacitor is equals to 1 over j omega c. So if your frequency is high, so then this ZC is actually converge into zero. So then it means like the introduce or induce capacitor, induce impedance of the capacitor converge to zero. So you have a kind of a very low resistive path for high frequency signal. So then what happens is like due to this bypass capacitor, so whatever the high frequency signal component appearing this emitter is simply grounded to this capacitor. So this capacitor is short circuited while once you have this high frequency signal. So then if you have this kind of a noise appear in the emitter, so this bypass capacitor is simply suppress or remove this high frequency noise to making it ground. So then you will get this pure signal here. So whatever the random high frequency noises are simply grounded through this capacitor, because capacitor act as a short circuit element in high frequency signal domain. So then the emitter is getting, emitter resistance is getting the simple amplified version of the signal, and whatever the noises introduced by itself is simply absorbed through this bypass capacitor, which connect to the circuit in parallel with the RE, or the emitter resistance. So through this bypass capacitor, we can basically remove this noise component appear within the circuit due to thermal noise or any kind of imperfect implementation of this hardware. So this is the real reason of having this different type of capacitors in the circuit. And then you may have a kind of idea about why we need different type of capacitors to couple the circuit. So these again, like there may be another reason, like for example, so we know that there is a particular current gain for the transistor. So let's assume like if we have a transistor circuit, so if you input a kind of a signal, so you get a kind of output. Let's assume you have a gain of 10. So what your requirement of gain is like 50. So what we can do is we can cascade these kind of amplifiers. So cascading means we just connect in a series. So you have this first amplifier having this gain. So then you connect it to a next one, then connect it to the other one. So then this introduce a 10 gain of 10, this introduce another 10, 10. So likewise, once you connect the fifth one, so you get the entire gain of 50. So this is the cascading of this amplifier. So ultimately, we'll basically get a 50 as an entire overall amplification. So overall amplification. So our requirement is a gain of 50. So, but whatever the transistors readily available in the market having the gains of 10. So what we can do is we can have a transistor circuit and cascade that similar type of circuits, cascading 5 units will give a kind of a overall gain of 50. So this is the cascading amplifiers. So this is a cascading amplifier. So you can simply connect those blocks in series to achieve a kind of a higher order gains. So what happens if you directly connect these cascading elements? So we know that if we basically introduce a small DC offset here to the, so let's assume you don't have any coupling capacitors here. So then we know that it's amplified and appear here. So this amplified DC offset is again fed to the next amplifier. So then this amplified version is further amplified and appear at the output of the second stage. So likewise, if you just directly connect these amplifier blocks in a cascading manner, so whatever the error initially introduced to the system is simply flow along this cascaded system, and ultimately you will get a kind of a huge DC offset, huge error, a kind of a significant distortion at the output. So what we can simply do is we can introduce coupling capacitors here. So then whatever the error introduced by this input is never fed to the first stage, and if there may be a kind of a DC offset incurred by the first stage, so we can simply block through this capacitor, so it never harms to the biasing point of the second stage. So this is a kind of a pure amplified version, and so you can then simply flow the actual amplified version along this cascaded system, and you can get the real amplified signal here without any distortion. So this is that's why we call it as coupling capacitor. So if you want to cascade multiple amplifiers to gain increase the overall gain, so you can just have this kind of a coupling capacitors. So this is the real need of having two types of basically capacitors: coupling capacitors and bypass capacitor. So next time we'll go through this AC equivalent circuit. So how this transistor circuit behave against this external AC signal. So this the behavior of the transistor is slightly different than the DC domain. So we'll basically discuss the behavior of transistors in AC or high frequency or low frequency domains next time. Okay, thank you.